Yeah, hello everyone. It's our pleasure to have Supanut over here to share about his nice work, exponential concentration in quantum kernels. So he's an expert in bare petals, and he just basically found the similar behavior in quantum kernels. And today he'll be able to tell us more about that. And Supanut, the floor is yours.
Okay. So thanks Bengi for inviting me. And thanks everyone for coming. So I'm Supanut. So before I was doing my PhD in Singapore and then like postdoc in Switzerland with Zoe, and now I'm back to my hometown country in Thailand, taking like a position at Chulalongkorn University. And so yeah, before we get things started into science, so that is basically the picture of our university in Bangkok. So if anyone in the audience, including Bengi, are interested in visiting us at some point, just drop me an email and we can try to figure things out. Okay. In this talk, I think I have two main parts. The first one is gonna be like introduction to QML and basically introducing this exponential concentration issue in rational quantum algorithms. The second part, we're gonna be mainly talking about quantum kernels, but I'm gonna keep mentioning the connection to other QML models as well. Okay, so let's jump right into that. Okay, so let's just basically trying to be a bit more precise about what I mean when we talk about like a machine learning model. Uh, so in this talk, it's simply going to be just like a function that depends on some tunable parameters, right? So I'm not so sure if you can see my mouse movement.
Yeah, we
Thingy?
can.
Yeah, okay. So basically you have function in that form, right? The f is basically the form of the function is going to tell you about what would be your model, right? The theta is your trainable parameters. These usually get adjusted and optimized during the training phase with some training data. And then this model is going to take some input data X. Okay. So for completeness, like if you do the classical ML, the linear regression could take that form, right? So you have theta 1 and theta 2 as your tunable parameters, and the function is just like a linear a linear line. And for more advanced step, you could think of like classical deep neural networks. The model here just like a linear transformation, and parameters you just have like weights and biases of your network. And okay, so just to be precise, when we talk about QML here, we just meaning that your model has some parts involving the quantum computers. Like for example, you might imagine about like a parameterized quantum circuit where you have part of it to be like your encoding data, and then you have like a tunable unitary, like parameterized unitary. And for example, you could just think of it as like a expectation value with respect to some observable as your model prediction. Okay, just for completeness, why do we want to build like a quantum machine learning model? So when you have like classical computer, you build your model that depend on some parameter, you have data, you can train your model, right? And then after training, you have trained model and you hope to have it such that it could perform like good on unseen data. So you could see that there's some accuracy being involved on like unseen data. So when we talk about quantum machine learning model, you just replace your classical with quantum. And here, the main reason why we want to do it is we hope to gain some advantage, right? For example, you could might hope to have like a less training data, but at the same time achieving like a larger accuracy, right? So this would be good for us because that you use less resources, but you predict better. So okay, I think that like a big motivation for us to do like quantum machine learning. So let's go build one. The problem is it's not super easy and super straightforward to do. And as the field progresses, we recognize that there are like a tons of issues, right? That these are some lists. It's not everything, but like here just some example. In today's talk, we're going to focus about like just this last one, right? Exponential concentration or barren plateaus. And the main reason behind why this one is quite interesting in particular is that it's a issue in the sense that it's a scalability barrier to your QML, right? You might be able to build your machine learning model on quantum computer for small scale, but then if you have like a barren plateau issue, you will not be able to scale it up. It's quite easy to come across in practice if you are not aware of this issue. And lastly, it's like it shows some fundamental limitation about what it means to incorporate like quantum mechanics into data analysis. Okay, but to really understand like how exponential concentration coming from, we might take a side step and look into this like a very closely related subfield, also called like a rational quantum algorithms. I'm sure many people in the audience heard this one before. It just basically you have some loss function. The O is observable. It defines the problem that you want to solve. For example, if you want to do like chemistry problem, your O could be the molecular Hamiltonian that you are interested in. The U zeta, just like your parametrized quantum circuit, is basically telling you how you want to solve it, right? And just by the form of the loss function, you can see some similarity between VQA and QML already. And in fact, that's like a big overlap between the two fields. Just for the completeness, the algorithm goes as follows, right? You have the parameterized quantum circuit, you measure expectation value, and you want to minimize this loss function. This loss function give you some like loss landscape that look that form, and then you measure it, and then you optimize it using your classical computer. So you have this hybrid quantum classical feedback loop. And of course, it's subjected to the same criticism. Does the algorithm scale well with number of qubits? And yeah, there's this big issue of like barren plateaus. And it is basically when your loss function landscape look like the picture on the right, right? So this one, so on the left is like when you don't have barren plateau, right? You have some features in your landscape. You can start somewhere and then you go downhill. You can optimize to the solution. So on the right is when you have the barren plateaus, everything is flat. It's actually not completely flat, but it's like you can still detect there's still some gradients, but the gradients are exponentially small, meaning that you need like exponential resources in order to navigate through the barren plateau landscape, and that just simply impractical, right? So you definitely don't want to be into this scenario. So just more like putting more into more formal definition, you might define barren plateaus as the following, right? So if your loss function is concentrated to some fixed some value that independent of your parameter zeta, and if you just like go over the landscape, and the chance of you finding this to deviate by delta is exponentially small, so your beta is exponentially small, then you're saying that you are in this like a barren plateau landscape. Okay. One way to detect or diagnose this is to look at the variance scaling of your loss function over the landscape. So if your variance is vanishing exponentially with the number of qubits, so it's going like that, and of course here B, here's a typo here, right? B should be larger than 1, otherwise things blowing up. Sorry, so that's the typo. So if things going down exponentially like that, and if you plot the number of qubits and the y-axis is like the variance, you're gonna see a graph like this. So if you dig down a bit, like if any of you have like go through papers doing analysis on baryon petals, you're gonna see this graph like very often. Okay, then you could ask like, okay, what is the main reason to what caused this baryon petal or like exponential concentration? And I think like people realize by now that it's actually just coming from like curse of dimensionality. And the way you see this is just by writing your loss function in the vectorization form, right? So you have that, you could write in vectorization form like this. So your loss function is actually just inner product between two exponentially large objects, right? And baryon petals coming from you not properly handle these exponentially large objects, right? So if you imagine you have vectors in large qubits, in large vector space, you pick two random vector in that space. The inner product between them is, if you pick things at randomly, the inner product between them is going to be in the order of like 1 over d, where d is the dimension of your vector space, right? And here is because we live in this exponentially, these objects live in the exponentially large vector space. When you compare them, is the inner product between them exponentially small if you don't, properly handle them, right? So the cost of baryon petals, you could think of it as like how many ways you can have like mess things up, what like, how many ways you can improperly handling these objects. And people be looking a lot into this. You can have this form like a too expressive circuit that you have. You could have like too much entanglement. The choice of target state that you want to learn also cause this, like the form of the loss function, globality, noise, and that there are basically like also link between simulation and absence of BP. Something people tend to look more recently is the warm star you initialize near this like a nice region. So it's just like an on passing, right? So things might get a bit too intense. So there are a lot already. And if you feel that it's too intense, don't even know where to begin, we have some very nice review for you. So feel free to check that out to learn more about stuff. Okay, so that is the first part of my talk. The second part, where we actually going into the quantum kernels and like machine learning models, is we're going to be asking this question, right? Basically, we know a lot about baryon petals in the VQA setting, how much it generalized into QML setting, right? Because the quantum machine learning framework are generally more complicated than the VQA. You have data set here, you have nonlinear loss function in some cases. Bilinear here, I mean like in VQA, you just optimize this expectation value, right? Trace or row theta. In the QML, the loss function might not take this form. And you could also optimize everything entirely on your classical computers. And so that things could be seen a bit different from VQA. And the question that we're asking here is like, how much one going to translate from 1 to 2? And what you're actually going to find is that this problem of exponential concentration is everywhere, but how it manifests can be subtle, right? What I mean by that is just by changing the framework, or like the like some part of your model will not just give you a free path to circumvent this problem of exponential concentration, because at the end of the day, what you're actually doing with QML is you're going to do like this handle exponentially large objects in the Hilbert space anyway. Okay, so we're going to talk about the kernel mainly in this talk, but I just want to mention that there are like others QML models as well, and we've been studying through those models. What we found is like, as we said, exponential concentration It's everywhere. It's in the supervised learning with parameterized quantum circuit. It's in quantum theoretic models. And okay, so now back to the main part of it, which is quantum kernels, right? And I should start by just introducing what kernel method is, right? So the kernel method is basically you have this data space, you have some data, and then you use you project it into the feature space using some like a feature map. And in quantum kernel, this feature map is your data embedding unitary, right? So it's in this form, and each individual data point X is going to map into some data embedded state. And quantum kernel is just basically similarity measure between two in the data encoded states. And the reason we call it quantum kernel is basically this function that measure the similarity is evaluated using quantum computers. Okay, so you could think of many ways to compare the two quantum state, right? One classic one is to just do like fidelity between the two quantum state. And we actually gonna stick with this example throughout the end of the talk. But in the actual work, we also analyze another form of quantum kernel. It's called a projected quantum kernel, where what you're actually doing is instead of just doing fidelity between two quantum states, you're doing like you project into like a smaller subspace, and then you compare them there, and then you collect kind of like you do this a couple of times, and you just measure the similarity by like collecting collecting of like the comparison on the some small subspaces. Okay, just coming back to this, the main reason people look into this quantum kernel is because when you train in kernel-based model, the loss landscape is generally convex, meaning that given the gram matrix, which is just the kernel values between all the input data pair, the training data pair that you have, if you have access to this gram matrix and then you train your model, you are guaranteed to have an optimal model that minimize your empirical risk, right? So for example, in the binary classification, I have the hinge loss function of this form. And what I'm doing here is that I just like minimize this loss function. And you can see that in this loss function, all I have to know is this Kij, right? Which is the elements of gram matrix. And if I know everything about Kij, I just chuck it in, I optimize this loss function. The final parameters are guaranteed to be the optimal ones. Okay, and it's very nice to notice that this the quantum computers are needed only to measure this gram matrix, right? So once you have this gram matrix estimated from your quantum computers, you don't actually need quantum computers anymore. The optimization is done classically on your classical computer. So you get rid of this picture of like a hybrid classical quantum loop. So you don't need to go back and forward anymore. And that, this, although like we're talking mainly about quantum kernels here, there are also other like QML model that using like a disparate, meaning that you measure first and then you training later, and all the model parameters they are in the they are not directly in the quantum evolution, and it just give people some kind of hope that you could maybe like circumvent this problem of exponential concentration. And let me just introduce this optimistic Mudeng. This Mudeng is great. It's from Thailand, and he's very happy. He want QML to work, right? And so he basically asking this question that I just mentioned to you, because what we actually have in here is there's no parameters in the quantum evolution. So the setting is totally different. And you might think that, okay, if we consider this setting, you might be able to get rid of the exponential concentration. And I hate to say this, but like, sorry, Mudeng, things are not going as smoothly as you think, because in this work, we analyze this concept of exponential concentration. But here, instead of over parameter space, you can have it over your input data space, right? It's mainly at this step when you need to do the data embedding from your data space to the Hilbert space, right? If you don't pick your data embedding good enough, you're going to get into this problem of exponential concentration. And it's very similar to what you had before. But instead of having it as your zeta, here you're going to have it over your input space, right? So it's the same interpretation if you have, and also the same typo. So if you going over the different point on your input space, you do the mapping, and your kernel where you concentrated toward a particular value, mu, we're saying that it's exponential, you have exponential concentration. And furthermore, if this mu is being small, here it's like, it's in order of 1/2 to the n, as if you consider like a global fidelity quantum kernel, you tend to have this to happen. So it's like your concentration point also vanishing. So we're saying that you will have exponential concentration towards some exponentially small value. Okay, so in this work, we're looking into two main aspects, right? What could cause this exponential concentration? So what going to get you to here? And also, what is the consequence of exponential concentration toward the your kernel methods, right? Because like, as we mentioned before, when you're doing the training on your kernel, things seem to be like going quite smoothly. You seem to have some like kind of like trainability guarantee. So what the heck actually happening here? Okay, and so the first part is very simple, because you can already see it, because like what we do here is you replace x and x prime, you replace zeta with x and x prime. So it's the same thing that you have curse of dimensionality, meaning that whatever could cause baryon plateaus in the typical like parametrized quantum circuit setting would also cause you exponential concentration over your data space when thinking about like doing the data embedding. Okay, so you have the same old culprits. You have expressivity, you have global measurements, entanglement, and noise, and all other stuff. What is quite interesting for us is the consequence of exponential concentration. What we're going to show you here is that if you have exponential concentration, you can actually train your model, but your trained model is going to be data insensitive. And this coming from taking into account the short noise effect, because these kernel values, you don't have it exactly. You can only estimate those values. So that's, and that consequently cause you to have data insensitive model. And again, it just basically the precision is costly in quantum computers, right? And because your kernel can only be estimated with measurement charts, and let's say n, and here let's say if I want to do fidelity quantum kernel, it's basically the fidelity between two data states, right? You have it like that, and so in practice you don't have this exact value. You can only estimate this one using measurement outcome. So it's going to be of this form, right? So the estimated kernel value is going to be the sum of your measurement outcomes divided by the number of measurements. And for example, you might think of, okay, there are two ways of measuring this outcome. The first one is just overlap test. You start with ux prime, and then you just estimate the probability of 0-bit string. Or you could just do the swap test, which is basically you have you run this circuit, and then you measure the expectation value of C here. And as just gonna do like a good professor here, is basically we're going to do this one swap test. The first one is gonna be left as an exercise for the audience. So please go and do the homework. Okay, so for the second one, right? So in the swap test, because we actually measuring the expectation value of C parameter. So your lambda can be +1 or -1. And if you work out all the math here, you just like chuck thing in here into that. What you actually having is that the probability of having +1 is 1/2 plus the kernel values, and -1 is probably of 1/2 minus kernel value. And the problem here is that if you have exponential concentration toward the exponentially small value, your kernel is going to be exponentially small with like high probability, right? You can show this, that the chance of this happening is exponentially close to 1. Okay, so what does it mean here? It means that the outcome of +1 and -1 in case of kernel distribution, and if you compare that one with the data independent uniform distribution, which is like 1/2 and 1/2, you know, these two, like lambda I and lambda I tilde, these two random variables, they look almost indistinguishable, right? Basically, if I just give you some measurement outcomes of plus and minus, of +1 and -1, and I ask you whether it's from the uniform distribution or the kernel distribution, you cannot decide. And that is just basically because your kernel values here tend to be exponentially small, so you can think of it as like you have like super small perturbation toward this uniform distribution, and you just cannot distinguish whether the sample coming from A or B. And that, so this is like the intuition behind it. So the way to put is like more properly is that you can use this like hypothesis testing. You can ask basically that same question, and you can, so in this work, we actually use this framework to show that in the presence of exponential concentration, the estimated kernel values are statistically indistinguishable from those evaluated from like a fixed distribution. So in other words, you know, your estimated kernel values are like statistically independent of input data, right? And which mean that what you're doing after that, which is like post-processing this estimate, it just, but see, like this kernel estimate, they don't have any information about input data. What you're doing after that is simply like playing around with like information-less values, right? And of course, you can train it, you can construct whatever it is, but in the end, you're gonna have like a data insensitive model. And it's just coming from the fact that your kernel, your estimated kernel does not have enough precision, right? So straight off the bat, it shows you like a bad generalization. What interesting more is that you can actually think like ask a bit more sophisticated question. Is it like, what about trainability, right? Because we just said before that you could have like the kernel where you actually have like a trainability guarantee. And here in this work, we also look at the into this. So we look into this like a rich regression example. So in this one, you can actually have the optimal value of your parameter written in the analytical form. And what you found is that the you have the graph like this, right? So the target function is like that, and the red points are your training data. And what you actually having is that the your prediction on the training data actually, your model can actually have the perfect training, but that doesn't come from like your model learning any hidden pattern in your data. It's just coming from your model memorizing the true label from the training data. Okay, and it's actually the generalization error in the very strange way. So we look at like a cook up example of learning task in the sense that we can show that so because like generalization error in general, you would get around it by just increasing the number of training data, right? So that what we actually cook up in this example, that you have exponential concentration. If you have infinite precision, you can actually train by increasing the number of input training. But because the effect of short noise, the estimated values that you have, if you train the model with estimated value, they don't improve by simply increasing the number of training data. So yeah, I think that pretty much wrap up the main messages of the work. So the source of concentration is the same as Baron titles. If you train under the presence of exponential concentration, yeah, you can train it, but the train model is data insensitive. And before I finishing it, I finished everything. So we also have like a follow-up work in other QML models that have no like a parameter that are in the same spirit as the kernel as well. So here's the extreme learning, and we're also looking into like quantum reservoir computing here, because the model, they make use of like the what people call like the random reservoir. What we show in addition to the kernel work is that if you have two random reservoir, you can actually get you into this like concentration regime. Okay, so I think the main takeaway message from the talk is just like, exponential concentration can arise if you being a bit like ignorant about what's going on, and you just think like everything is going to work if you just add quantum everywhere. So basically that's what we show, is that there might not be like one QML model to rule them all. And whether your model suffer from the concentration is actually, you should think about what you actually measure in order to construct your QML model. And then you ask whether the quantities that you measure, they are concentrating or not. And exponential concentration is everywhere, but it's not everything about QML. You have other problems, other challenges, other opportunities to consider, like local minimum, or like what would be like good learning problems. And yeah, so people also show that if you encoding the learning problem structure good enough into your QML model, you could actually have like the approval advantage. And so I think that's the end of my talk. Here are like my lovely collaborators, Marco, Zoe, like Manuel, Sasha, and many more people. So yeah, and I think that's the end of the talk. Thanks for listening.
Yeah, thanks for the very interesting talk with a lot of memes inside, especially the mooding, as we have the screen over here. Yeah, so for the audience, if you have any question, feel free to unmute yourself or type a question in the chat, and then I could help you to ask the question. In the meantime, I could ask a couple of questions over here. I think maybe you can go back to your slide about the accuracy doesn't improve if you have more shots over there.
This one?
Yeah.
Yeah.
So over here you mentioned that okay, it's not really the accuracy couldn't be improved by more input data, or generalization or things that you like it, right? But is it possible to observe this because you just have too less of the input data points? Because I could imagine some kind of transition if you have a lot more training data points. Like let me kind of like describe a bit more. So imagine you have exponentially many points that you can observe, but then just like, for example, just have one shot. And there's some chance that you might land on the similar points. And then as you increase the number of points, even though you have one shot, uh, like the likeliness where you could have it landing on the same point or the closer points will increase, and then it might give you more and more information, and then you might be able to learn more about the overall kind of like kernels by learning the near varying points, right? Would you expecting this to be
So I
occurs
think
over here?
like the problem here is that like regardless of how many number of shots that you do,
Mm-hmm.
okay, you could. So the thing is that when you do the measurement, right, what we actually show in the theoretical result is that if you have like polynomial number of measurements, then the chance of those measurements contain any information about your input training data is exponentially small.
Mm-hmm.
So meaning that it just like your model does not have any clue at all about your training data.
Right.
You could think of you could trade that maybe with the exponentially number of training data. And so if you have exponentially many training data, you might have a chance that one of those is now it's like is you playing around with like exponential versus exponential, right?
Yeah. Yeah.
If you have exponential data, what we're saying that for each data you might have like an exponentially small chance of uh, observing any information. But if you have exponential data, then you just maybe one of those could give you something. But
Mm-hmm.
but even that is impractical, right? It just we're
Yeah.
trading one exponential for another. It's not good. Yeah.
Yep, I see. So over here, practicality is the king. And we have to take the reality into account of polynomial short or polynomial number of data points.
Yeah. Yeah.
Mm-hmm.
Yeah. So I
Yeah.
think that's the thing that I like most about this part of the work is we really think about like what would be the practical setting, right? What would
Mm-hmm.
people actually going to do in the lab, right? And it is the practical consequence of what if people actually just go to the lab and cook up the kernel methods model using in the presence of like exponential concentration.
Mm-hmm. Right. So do you think there's any path to go forward in terms of like quantum kernel? Yeah, because like for exponential concentrations, there are quite a lot of things for us to take care of, right? So
Oh,
um
I mean, you probably know the answer already. But thanks for asking. I think I want to highlight the last key takeaway messages here, which is basically people show that if you actually look into like a good enough quantum problem, by quantum here I mean like good enough problem that you should be able to solve with quantum, and then you encode enough like problem structure into building your QML, you can actually have like a provable advantage. So actually like this paper, uh, the the model that people consider in this paper is actually a kernel method. Uh, so yes,
yeah.
that's a way to move forward.
Mm-hmm. So there's good news to hear. At least like there's some kind of like pathway that we can like go away from this. Yeah. And so yeah. And then would you expect some new type of like QML model will come out? So because like currently the dominant one would be like quantum neural network and quantum kernel methods, right? Like were you expecting something new to come out, or we just currently just like stuck with this two? Or do you have any thoughts of what kind of new model we could have? There's this very generic question that just throw on you.
Yeah. I don't really know actually. I
Right.
think that's a very good, interesting open problem.
Uh-huh.
Uh, I mean, like people just tend to. Uh, I think we should just keep exploring. Yeah.
Mm-hmm. Yeah, because I've been doing quantum neural and quantum kernel for quite a bit, and yeah, just a bit clueless of like what kind of like near-term QML model that we could have. Um,
Oh, I have opinion on that one. I think
mm-hmm,
like when people say like a near-term QL model,
mm-hmm.
I think it might not be that super near. Uh,
Oh,
like
okay.
yeah, like I always more and more recently, I always think of like QL as something you want to do even in like the Fortran regime. Uh, yeah. So one interesting way to move forward is like how much can you actually utilize the knowledge of Fortran quantum algorithms to build your QML model. Um,
Knowledge about fault tolerance, what do you mean by that?
like quantum phase estimation, uh, along that line,
Right,
Grover, uh, because those algorithms they seem to be working quite nicely, right? There's people love to use them, and I think we don't take like enough thought. We don't think enough about like how we can utilize those algorithms in QML context.
right. So, not too sure. Have you kind of like fully just like go? I think you kind of like know the work. So I just like bring it out anyway. So I think like Maria should have already kind of done in a similar fashion, right? They try
Yeah.
to utilize like quantum Fourier transform. Uh, so what do so essentially what you mean is trying to
So more of those basically. Yeah.
more of those, right? Trying to see out like with that like what kind of like true quantum oracle that we can use and Ethereum brings like quant that will help us to solve meaningful problem using quantum computers.
Yeah.
But do you expect us to use variational algorithms in the fault tolerant regimes? Or
Why not, right?
mm-hmm,
Um, yeah. I don't think. Okay, so it's like when people say like VQA is near term, I don't think it's that like super near as like many people think it would be.
right.
Um, yeah.
So so you think that we still need to have some kind of like good logical qubit in order to do variational stuff.
Yeah, yeah. Because noise is going to kill everything otherwise.
Right. I think it's like nowadays like people okay, maybe I didn't talk to too much of people, but currently they don't really talk about the noise induced type of things that much now, right? Is it because version are just going downhill or like what do you think? So or maybe now we're just focused on photon and quantum algorithms.
Yeah, okay, so I think like one good reason people don't talk much about noise in the context of VQA because but I think it's just that people already know that noise is bad. Uh
Mm-hmm.
so you so it's like noise is bad. Uh then you could ask like then what would be like a good questions to tackle with VQA, or is like how we going to tackle it. So one thing we know for sure is that you don't want to have a lot of noise.
Mm-hmm.
Yeah,
Right. So basically just because we already know that noise could be bad, so then we just say with less noise that we can do this and not going
yeah.
to talk about it anymore. Okay, and uh, maybe we could ask a final generic questions. So over here you basically investigate a lot about shorts, right? And see how the number of shorts and number of measurements could affect the accuracy or the generalization errors of QML model, do you think the short noise will play a role in the kind of like fault theorem type of QML model that you mentioned just now about like using Grover or quantum phase estimation or quantum Fourier transform? Do you think that there's an
I think like for those problems, because like some of those you actually just measure one bit string at the end,
mm-hmm,
as compared to the expectation value in the case of like VQA. So
mm-hmm,
I think um the short noise problem is gonna be much less severe there.
mm-hmm. Right. Okay, nice. Um, so I think we should yeah, we have a nice talk over here, and I will just like post this on YouTube. People might just like go and email you to ask more about questions and things like
Or
that.
if people want to come and visit us.
Yeah, definitely have to highlight it. So people who are interested to visit Supanut or Chulalongkorn University or to see modeling, feel free to email Supanut. I think you have the emails on the papers,
On the
right?
first page. Yeah, on
Yeah,
the first page.
yeah. First page. Okay, cool. Then we have a good
Yeah.
connection contact. Uh, yeah, I
Uh,
just like flashing through all the memes again. So
yeah. So this is
yeah,
like the last flashback to everything.
yeah, last flashback
Uh,
maybe and C3
oh
tree
damn.
modeling.
Uh, yep.
Yep,
Here you
over
go.
here. So now it's just your Gmail. Cool. Okay, then thanks again to Bernard and thanks everyone. And
Yeah.
see you
Thanks
guys next
everyone,
time.
and thanks Maggie again for inviting me. Uh,
Yep. Cool.
bye bye. See you all
Right,
later.
see you.